Okay, let's look at some example problems for Module 1 for circuits. So the first problem I want to look at, let's say we have 2 meters of wire, so we'll call it number 1. 2 meters of wire, and say it's copper. And let's say that it has a diameter of 2 millimeters. And for some reason, we got a little wall wart thing plugged into our wall, AC, and it produces 9 volts AC. Alright, and so we want to know how much current, we want to know what is the current and what is the charge. That we'll go through this wire if we do this kind of probably stupid thing. Alright, so don't do this at home, just take a piece of wire and connect it across batteries. But we're going to do something like this. It's not a battery. Plug it into the wall, so that's even worse. AC is more dangerous. So don't do this at home, but let's make up a problem and see how much current there is. See if it's more than 20 milliamps that can kill you. Okay, so what do we need to know? We're talking about voltage. Yeah, 9 volts, that's a 9, okay, what is that? 9 volts, we got voltage, we got current, we got charge, we've got a wire that's going to have resistance, so we're going to need a couple of laws. So one thing we're going to need is just the equation for how do you get resistance from parameters of a wire. So it's rho L over A, where rho is a resistivity, A is a cross-sectional area of the wire. So if this is the wire, it's got a cross-sectional area A in there. L, of course, is the length of the wire. R is its resistance. We also need Ohm's law. It says V equals IR. Remember our good old Ver friend to relate V and I to each other, and R. And then just from the definition of what is current, we need I is dq dt. Remember that also to get back to charge probably. Okay, so first things first, I think we need to find the resistance, because if we want to get the current, we got voltage is given. Voltage that we're applying to the wire is 9 volts. At least magnitude, we'll just do this, we'll probably write it out as a function of time. So magnitude-wise, it's 9 volts. As a function of time, usually we write that as lowercase, it's going to be 9. We can take sine or cosine, let's just do cosine. And omega t, omega is 2 pi f. F is 60 hertz in the United States, so that's going to be 377 for 60 hertz. So let's just go with that. And this is volts. All right, so it's a sine wave. What's in our walls, all the AC power is sine waves, and so we could pick sine or cosine, but let's just pick cosine. Or I don't know why. Okay. Then we want to get the current. So even in AC, the current is going to be V over R. Rearrange this equation. So we get I is V over R, or I as a function of time is V as a function of time divided by R. So we need R. R is rho L over A. We need to look up the resistivity of copper. I just happened to have looked that up a little while ago, or found it on the homework assignment. 1.72 times 10 to the negative 8. Ohms, it's kind of got weird units given in the homework assignment, but just because of, it's really ohms times meters, but that's a weird unit, but it's ohms, it's meter squared over meters, however you want to write the units is fine. Okay, so, but this tells us that we need our length in meters and we need our area in square meters. Maybe that's why it's written that way, I don't know. And so we need A, just use this little sidebar for finding the pieces we need, because we got L, I said it was 2 meters, so that was L. But we need A, area of a circle, pi r squared, pi d over 2 squared. So in this case we got pi times d was 2 times 10 to the negative 3 meters. Divide that by 2 squared. So 1 times 10 to the negative 3 squared. So we got pi times 1e negative 3. No. parentheses in the right place. We're doing our squared. There we go. All right, looks like we got the right thing squared. So we get A is 3.14. 2, we'll go keep an extra sig fig, 10 to the negative 6 square meters. Okay, so I think we've got everything. So we'll put in row 1.72, 10 to the negative 8 ohms meter squared per meter. L, 2 meters. Even though it's a long piece of wire, it's still going to have very small resistance. And then A, 3.142, 10 to the negative 6 square meters. So everything cancels out except for ohms, which is what R should be in. So 1.72 E negative 8 times 2 divided by 3.142 E negative 6. Okay. So we get, we'll just call it 10.9 E negative 3, so milli ohms. Alright, so I of t is then just 9 over 10.9 times 10 to the negative 3 cosine 377t. But now it's going to be amps since we got volts over ohms. 9 divided by 10.9 E negative 3. Woo! Yeah. That's why you don't want to play with this. 800, and this will burn up the wire just like nothing flat. Okay, 826 amps. Whoops, 826 is the peak cosine 377t amps. So definitely not something we want to try in real life. Okay, it would blow circuit breakers and burn, anyway, it would be bad. All right, and then, so we got I, actually we should have said I of t, and then we want Q as a function of time too, so let's write it like this. Okay, so let's remember our equation here. So Q as a function of time then is going to be the integral of I dt, or antiderivative, however you want to look at it. And so we wanted to keep it kind of general. I guess we can let's just do the antiderivative. So then we're going to have Q of t is going to be integral of I of t right here, 826 cosine 377t dt. And so we could put in limits and get the exact, but we want this kind of a general equation, so we're just going to do the antiderivative and leave like a plus c, or it might be like a q naught kind of a thing would be there. So Q of t, what's the derivative of cosine? Negative sine. We got internal thing here, so we have to do the chain rule, derivative of the inside times the derivative of the outside. So the derivative of the inside, integral of 3/7. Do we need to do, well, let's just do a little more, let's just do a u substitution, just make sure we do it right. So u is 377t, and so du is 377 du, so we get the integral of, what happened here? I need a dt. And so dt is du over 377. Okay, and so let's substitute in for u. So we're going to have 826 cosine of u du over 377. Yes. Integral of cosine is negative sine, and so we're going to get negative sine u times 826 over 377 plus some constant of integration. All right, and then we plug back in what sine u, or what u is 377t. What's 826? 826 divided by 377. 2.19. So we're gonna end up with negative 2.19 sine 377 t plus some constant of integration q of t. And so if we want to say that at t equals 0, we knew that the charge was 0, then we could, sine of this is going to be 0, so then q naught is 0, and so you could just have it be sine wave. Generally, we would anticipate it being a sine wave. So if the voltage is a sine wave, the current's a sine wave, the charge is a sine wave, everything's sine waves. Okay, the DC parts would be canceled out or gone, or not existent in the first place. Okay, so that was the first one I wanted to try. First example. Let's look at another problem. Some made up problem here. Let's try this circuit here. So we're just gonna do some KCL practice, Kirchhoff's current law practice. So we have a circuit, just making all the elements look like boxes. They could be sources, they could be loads, who knows what, they're just stuff, elements. And so let's say we know the current here is 3 amps, and we are looking for the current here, I1, and this guy. Say we know the current here is I2, current through the middle element is 5 amps. We're going to call this one I3. Okay, so whenever you have a circuit like this and currents defined, or you're trying to define currents for yourself to start solving, which is a good step when you got a circuit to solve, you need variables to work with, so you need to define your currents and voltages possibly. You need to kind of just look at, well, let's just look at this node to start with. So let's call this node. So, well, first off, you need to figure out what are nodes. So nodes are places where wires elements come together. All right, so it could be a whole bunch of wire coming together, but it has to be between two elements or more, two or more elements. So let's start over here if we're going to start with the nodes. And so I've kind of put circles in certain spots where the nodes are, but really this whole thing is a node, right? All the wire that connects these two elements, we would call this node. Let's just call this node 1. And then let's say all this wire is kind of a T-shape because it's connecting 3. Let's call that node 2. Here's node 3. And then here's node 4. Sorry, I've got a kitten crying. Let me go take care of the kitten. So we've got our 4 nodes here, but 2 of the 4 are really kind of boring nodes, because when they only connect 2 things to each other, like we talked about back in physics, when they're only 2 things together, writing KCL doesn't make a whole lot of sense. But in this problem, it's defined so that you can kind of have to think about that, or anyway, hopefully giving you practice thinking about it. So at this node, at node 1, we do KCL at node 1. So normally I would say you don't have to do KCL at nodes that only have 2 things, but if you want to for practice, go ahead. So at this node, remember KCL says you can write it different ways, but one way is current in equals current out. That's the way I like to do it. So what's the current into this node? Which of these? So we got two elements. They're going to have 2 currents potentially, and so there's no current in, right? It's all 0. So we've got in equals out, but we got nothing going in. So one of them is going to be negative, right? And what's coming out? 3 amps is going out because it's flowing this way. It's going into this element, so it's coming out of the node, right? 3 amps is going out, and then also I3 is coming out. So this is just going to say I3 equals negative 3 amps. All right, and so hopefully you will kind of get to where you can just look at a picture and say, okay, I3 and 3 amps, they're the same thing, except for they're going the opposite direction, right? So current flows through thing. Whatever goes in one side of an element goes out. Current doesn't get used up by elements. Charge does not build up inside. In transient cases, in a capacitor, yes, but we're talking general steady state stuff. Current doesn't build up, charge doesn't build up, so what goes in comes out, all right? So if this kind of current is going this way through here, it's also coming here. It's all the same current in this one loop, all right? These 2 things are in series. They have the same current, and so I3 has to be, since the arrows are going the negative, this one says I3 is going this way, but 3 amps is going that way, so they have to be negatives of each other, all right? Same thing for node 3. Another one of those boring nodes, because what do we have coming in? So in equals out. We got coming in I1, going out is I2. So all it says is I1 equals I2. Yes, they're in series, they have the same current. So there's only one flow going around this. You want to think of it as a pipe of water or whatever, but there's only one flow. Whatever comes inside this one goes through that one, so I1 and I2 have to be equal. Okay? So, maybe for this module, go ahead and write KCL at these nodes, or at least write down the equation from looking at this node or something. But, as we go through the semester, if we see something like this, hopefully we'll just be able to identify, oh yeah, those are the same current. Maybe one's negative of each other, but we got it. Okay, so let's do one more case. And so once we've got that, maybe we'll see that nodes 2 and 4 aren't going to give us any different information. But so what are we trying? We're trying to get I1, I2, and I3. So we got I3 solved for as a number. We know that I1 and I2 are equal to each other, but we don't have numbers for those. So let's try to get some more equations. Let's do an interesting KCL. So let's do KCL at node 2. Okay? So at node 2 up here, we want in equals out. So what's coming into node 2? Just 3 amps, right? Only thing coming in. What's coming out? We've got 5 coming down out of the node. Remember, all of this is the node. So 5 comes out, and then we've got I1 also coming out. All right, so we can just get I1 must be negative 2 amps. All right, so we drew the arrow going the wrong way. That's okay, it happens. Okay, or else I made up the problem bad, but I think it's okay. And so I1 and I2, and so I2 is also negative 2 amps from here. All right. So, yeah, since there's 5 going this way, so it has to come from here. So one of these must be a source. They must be pushing current the other way. This is just totally made up. So anyway, that hopefully makes sense. A little KCL practice. Let's look at another example problem here. Made up something here with another circuit. So it's got a voltage source here. Resistor. What's this thing? Hopefully you recognize that as a battery symbol. So we're talking a DC circuit here. And we'll have some more resistors. Something like this. This is going to be a dependent current source. So when we have an arrow inside a source like this, it means it's a current source, and so it's having a fixed current. Whereas if we put the plus and minus inside, it's a fixed voltage source. All right, we can just call this VS. Let's say this is 3 ohms. Now this is a current source, but it's dependent. It's a diamond shape, and so that usually means it's a dependent source. So its voltage or its current depends on some other measurement in the circuit. All right, this one we're just going to say that the current here is 2 times the voltage Vx, and we're going to call this voltage over here Vx. All right, let's say this is a 2 ohm resistor, 5 ohm resistor, 3 ohm resistor. Okay, and let's say we are looking for I1, and somehow, magically, we know that this current is 2 amps. Okay, so we want to get the current over here. We know the current here, but we don't know the current from the source, from this battery. We could find, if we found the current here, hopefully you can notice that it's all the same current. These are all 3 in series, and so 2Vx is I1, right? If we can find that, we can get that. And let's go ahead and figure out what is V1 too. Let's call this V1 the voltage across this resistor too, just for fun. And Vs. Actually, I haven't solved this, but we'll see if I need more information or if we can solve it with just what we have. So we want to figure out what's going on in the top half of the circuit, basically, or this side. Okay, so what do we know? Well, when we have a battery like this, hopefully remember the long side is a plus and the short side is a minus. So we want to go ahead and put the plus and minus on there. We're given that voltage, so that's good. We're given the current here, which we didn't have to be given because we could just use Ohm's law here, but we can get Vx, right? So again, let's identify our currents. Remember this 2 amps. Let's identify what's in parallel, what's in series. So this whole side, these two are in series, right? We have nodes here, here, and here, but most of these 3 nodes are boring nodes because they're only joining 2 elements, right? So this whole branch is in series. This guy is not in series with anybody, he's just by himself, and then these 2 are in series. And then we've got 3 kind of parallel branches, one with 1 element, one with 2 elements, one with 3 elements. Right? Okay, so trying to solve for stuff, maybe hopefully you can see which one did I want to be the plus here. I've got 2 pluses on my, oh, that's a Vx. Okay, that's a Vx plus minus. There we go. So Vx controls this current source, so we should try to figure out if we can find what Vx is, which we can. Let's try to say how we know things or what laws are going to tell us stuff. So let's think about Ohm's law. What does Mr. Ohm say? Ver. Mr. Ohm says ver. V equals IR. V equals IR. In this case, since we know these are in series, the 2 ohm resistor has 2 amps of current. So we know it's current, we know it's resistance, so we can get its voltage. In this case, its voltage is Vx that we're looking for. And so it's going to be, Vx is going to be 2 amps times 2 ohms. All right, so Vx is 4 volts. All right, so we got the voltage here. We could also, if we want to get the voltage here, what does it have to be? V equals I times R. So this is going to be 10 volts. So that's good because we have, if we go up to get to this point, we go up 4 volts, go up 10 volts. So we got to 14 volts, which got to be the same as if we went from here to here. Go up from here to here, we should go up 14 volts. So those agree, so that's good. So that's why I'm saying we could have used this source to figure out that voltage as well. But we have a little bit over-specified problem here. Okay, so we got Vx, so we can get the source current, the current in the source, right? So it's going to be 2 times 4. There's a unit, this is going to be current, and so it's going to be 8 amps. Even though this is a voltage, sometimes we would call it a voltage-controlled current source, but the current is what is the output. Is going to be 4 amps going in the direction indicated. All right, and so looking at this, remembering these are in series, or these nodes, current in equals current out, current in equals current out, and so we can say, oh, okay, so I1 must be 8 amps. All right, just from this voltage source, or I'm sorry, this current source says that its current is saying what the current is through it, okay, and so the current through it has to be the current through this source and this resistor. It doesn't have anywhere else to go, so it is 8 amps. Alrighty, and then what else can we do? Can we find Vs? Can we find V1? We can find V1, right? So we can use Ohm's law again. It says V1 equals I1 times R, which is 3, R3, I don't know. So V1 is, I1 is 8 amps, and R3 is 3 ohms. So V1 is 24 volts. Okay. We can't get Vs. Yeah, I don't think we can get Vs from this information, or from the way I have this circuit put together. Why not? Well, so we know the voltage here. We know the voltage here. So we could try to name the voltage. Usually sources we have positive coming out, so we call this VI maybe for the current source. So put this, it's positive voltage where the current comes out. All right, so we don't know Vs, we don't know Vi. we know this voltage across here, so let's just try. Let's do KVL on the left loop, I guess we'll call it. Left loop. My writing is bad. Okay, KVL the left loop. So let's say start here, we'll go walk around, hit negative signs. We put a negative sign on the variable we find. So negative VI minus VS plus V1 plus 14 volts. So we hit the plus, and then we're back to where we are, where we started, equals 0. All right, so we got V1 is 24 volts. So we know that also. So the best we can get is VI plus VS is, so bring that to the other side or bring these, anyway, or rearrange, is 38 volts. Right, but we can't separate out VI and VS because we don't have enough information on those. All right, so maybe I should have said that this was a 12-volt battery kind of a thing. Then we can say that VI is going to be 38 minus VS, so it's going to be 26 volts. Okay, so hopefully that gives you a little practice. Remember your tools. You got Ohm's law, you got KVL and KCL, you got knowledge of sources, you got knowledge of series and parallel kinds of things to kind of get you where you need to go. Yeah, so we pretty much, with a little help of adding a little information here, pretty much solved the whole circuit. We got the voltage and the current in well, we didn't calculate the current here. Let's go ahead and get the current here. Let's call this I sub D, just so we can say we solved this whole circuit, and that's a capital D. I of this, so what is the current of that battery? We haven't named these nodes. Let's just call this node 1 since we don't have any nodes. So let's do KCL node 1. All right. What do we get? We get current. We want in equals out. So what do we have? We have I1 is going in. I1 is 8 amps. And we've got ID going in. What we're looking for. And that's all that comes in. There's no other. If we have 4 or 5 branches, we could have 4 or 5 currents coming in, or out. So we have just these two coming in, and what we got out is 2 amps. All right, so ID then, ID equals, okay, negative 6 amps. Which is a little weird, but when you've got dependent voltage sources, odd things can happen. We would expect that this source would be pushing current and making adding to the circuit, causing a voltage out, but because of the way this is set up, this source is actually sucking in current, right? So it's not actually producing power, it's absorbing power, right? Because it's got a negative current. So if we want to calculate the power of a source, we do V times that power, PIV, we got power equals VI, and so power would be 14 times negative 6, so it's actually taking in negative, what is 14 times 6? Taking in 84 watts, right? Whereas these resistors, current goes into their plus, so they are using up watts, right? So this one would be using up 10 times 2, so this one's taking 20 watts, and this one's taking 2 times 2, no, what was VX? 4. So for example, P of this 2 ohm resistor would be VI, VX times 2 amps, which is 4 times 2, 4 volts, 2 amps, 8 watts. All right, but it's positive, it's absorbing, because for resistors, positive is current coming into their plus. So same thing here, we named this one correctly. Well, it had a current of 8 amps and a voltage of 24 volts, so it's absorbing a lot of power. And at least this source is, I guess this source, these two sources are the ones that are putting energy in. This one's actually, I guess, charging up the battery. I don't know what we want to say there. Okay, I think that's all the problems I had for this module. So hopefully that helps you get your homework going.